Hi, I'm David and I'm the coordinator of the Maths Learning Centre. I've had a request from Probability and Statistics to students to talk about bivariate distributions, and I did a revision seminar on that already, but the recording failed, and so I'm doing another one for you to an empty room that I can upload so you can watch it. So bivariate distributions. Now, what specifically people wanted me to do was talk about the integrals, the double integrals across regions and the single integrals that you need to do marginal distributions, and how to choose what the limits of those integrals are. So that's what I'm going to do. And before I do that, I'm just going to have a quick talk about my understanding of bivariate distributions so that you can have a picture of what I'm talking about, and then I'll do some examples. So bivariate distribution, there's two variables, x and y, or maybe y1 and y2. And they have a joint probability distribution. And what this means is that every x and y combination has its own probability. Now, it would only really be a probability if it was a discrete distribution. Continuous distributions, it's more of a likelihood of being near that spot, but it'll do for the moment. I'll just put it in inverted commas and it'll be okay. That's the probability of this combination of x and y. Because I'm going to give you an example of one. It's a discrete one. This is my x, this is my y. My options for y are 5 and 6. My options for x are 1 and 2 and 3. And each of those combinations of options has a probability. So 1 and 5, and 1 and 6, 2 and 5, 2 and 6, 3 and 5, and 3 and 6, all those possibilities all have their own probabilities. So it's a sample space and they each have a probability, and all those probabilities add up to 1. So let me do this one. What if it's a quarter here, and a quarter here, and a sixth here, and a 12th here, and a 6th here, and a 12th here? So they're all supposed to add up to 1 if this is a valid probability distribution. Now a quarter is 3/12, another quarter is another 3/12, so we're up to 6/12. A sixth is 2/12, so 6, 7, 8/12, 9/12, 10, 11/12, 12/12. It does add up to 1. So what I want to do is I want to draw a picture of that. Normally we can think about this as a graph, only it's a 3D graph where each probability is interpreted as a height. And so I'm going to draw that graph with you, for you, using Lego. Okay. So I've got a quarter here, which was 3/12, and another quarter here, which was also 3/12. And a sixth here, which is 2/12, and then a 12th here, and then a sixth here, which is also 2/12, and then a 12th here, which is 1/12. Okay, so this is a picture of my probability distribution, my joint probability distribution. Each x and y combination has a height, and that height is the probability. There you go. That's the idea behind it. Now, if I was going to do what they call a marginal distribution, then I would add up all of the possibilities for x. So x could be 1 or 2 or 3. And if x is 1, well, there's this much probability attached to 1, and there's this much probability attached to 2, and there's this much probability attached to 3. And that there is the probability distribution of x, the marginal probability distribution. So what I've done is I've lumped all the probability together on the x's. On the other hand, hey. And this one was a quarter 2. So this is what it was originally. On the other hand, I could also figure out the probabilities of y by adding up this way. And that would be the distribution of y. Well, it's more formally this way, really, because that's 5 and that's 6. So there you have it. That's the idea of marginal distributions. Only one more thing to mention. If you want to add up the whole probability, one way of doing that is to add up the marginal distributions this way, and then add up the distributions in the probabilities in the other direction, and that would be your total probability. I've got 12 blocks, so really they all have to represent a 12th. And that's one of the concepts that we do when we do these integration problems. You go, well, the whole thing adds up to maybe 54, so I'm going to have to divide by 54 so that the total probability is 1. Mine adds up to 12 bricks, so each brick has to be worth a 12th. All right. Insert Lego here. All right. Just so if you're looking at it afterwards, you can see, you can know what I did on the video. Right. So that was just a philosophical idea there. Now with continuous distributions, everything's, instead of adding up, it's an integral, but the idea works the same. And also it's worth pointing out that when you draw this picture of what the sample space is, the probability isn't part of that picture. You have to imagine the probability being somewhere. So it's time to do an example. Let f of x and y be, I don't know, x squared plus 1 for 0 is less than or equal to x, which is less than or equal to y, which is less than or equal to, say, I don't know, 5. Or, I don't know, maybe not x. Maybe x squared plus x, y. Yeah, let's do that one. Got to have a y in there. Okay, and 0 otherwise. Only it's not going to be that, it's going to be some multiple of that, because the area that represents, the volume that represents, might not be 1, so I'm going to have to adjust it so it is 1. Okay, so this is a classic problem that you might see. Part A would be find C so that this is a valid probability density function. I could have fit that there, couldn't I? And then maybe part B would be find the probability that x plus y is not x plus y, just a second. Yep, x plus y is less than 3, for example. And then part C, maybe find the marginal distribution of, I don't know, y. Okay, so that's what I'm going to do. Maybe I'll find them, yep. So there are 3 things that you might want to be able to do. So, part A. Well, I know that the total air volume there will be 1. And so if I add up the total volume and it doesn't come out to 1, well, that'll tell me what the C has to be, and I adjust it to make it 1. But first I have to figure out the region that this works upon. In my example, my region was a nice rectangle, but this one is unlikely to be a rectangle. So I'm going to draw my region. Okay, so the region does not rely on this bit, it only relies on this bit here. So let's have a look at that. I have 0 is less than or equal to x, and x is less than or equal to y, and y is less than or equal to 5. And because the x is eventually less than 5, I can actually stick that in. And because the y is eventually greater than 0, I can stick that in too. Alright, this is what I want to draw. The quickest way to draw any region like this is to really cross out the bits you don't want. And so I'm going to draw two diagrams. Okay, so this is where x is 0 and I don't want it to be less than 0. This is where x is 5 and I don't want it to be more than 5. This is where y is 0 and I don't want it to be less than 0. This is where y is 5 and I don't want it to be more than 5. So that's great. And then the final thing is this one where x is less than or equal to y. Okay, well, the edge of that would be a line where x is equal to y. And x equals y is the same as y equals x. That's where x is equal to y. And I know that being a straight line, inequalities with straight lines, one side of the line will, the entire part of it will need to be crossed out because it's the wrong side, and the other side, the whole of that side will be the right side. So what I need to do is I need to figure out which side is the wrong side and which side is the right side. And the easiest way to do that is to sub in a point. So now I need a point that's not on this line, so 0, 5, 0 is a pretty good point into x is less than or equal to y. So let's see, 5 is not less than or equal to 0. If I sub it in, it's actually not true, and so therefore I have to cross out this because this point is on the wrong side. And just to check if I had chosen the point 0, 5, 0 is less than or equal to 5, and so therefore yes, that would be the correct side. So this is the region that I actually want. So okay, all the probabilities out here are 0, and this is the only place where there's non-zero probabilities. So let me redraw that. Oh, 5, 5, and that's the area I want. But I'm not actually calculating that area. I am calculating the volume that is sitting above that area. So what I can imagine, actually let me just redraw that on another piece of paper, bigger, maybe not that big, oh yeah. What I can imagine is that every point has a probability. And it has a height, and that height is based on this formula that I drew earlier, this formula here. So c squared x squared plus x times y. So over here x squared plus x times y is 0. Over here x squared plus x times y is 50. Over here x squared plus x times y is 0. And so it's 0 here and it's 50 up there. So there's going to be some sort of weird thing that curves upwards like that. Now you won't necessarily have Play-Doh in an exam, but that's what I'm just saying, that that's what my probability looks like. Okay, just so you can imagine what we're talking about here. Right, so my probability isn't actually on this diagram. There's some blob of Play-Doh above it which represents my probabilities, and I need to find the volume of that. And what I'm going to do is I'm going to do what I said earlier. I'm going to add up the probabilities along vertical or horizontal lines, like scoop them all down and add them up that way, and then add up all those answers. So I'm going to do it in this direction. So what I'm going to do is I'm going to imagine this vertical line here, and I'm going to add up a slice of the probability that's in that direction, and then that'll create a marginal distribution, and then I'll add up all of those ones in the other direction. So actually, just a second, since I was asked to do the marginal distribution of y, I should probably do that, really, I should probably do that one, that direction first, because that would give me the marginal distribution of y. I won't though, because I want to show it as a separate problem. Okay, so the x coordinate tells me where this line is. And that x coordinate is going to shift from 0 to 5. And as that x coordinate shifts from 0 to 5, the region here that I'm integrating across will move as well. It will go all the way up to 5. And this point here, well, it's on the line x equals y. So the y coordinate here will be 5, will be x. And at this point here, the y coordinate will be 5. So along this line, I go from y equals x to y equals 5, because it goes up and down in terms of the y's. And the line itself moves back and moves forwards from x equals 0 up to x equals 5. And that's how the integral is going to be written. The x is going to move from 0 to 5, and the one on the outside is the one that moves just with plain numbers. It doesn't have formulas. It just moves across the numbers, and that's where my vertical line is. And then once I've chosen my x, my y moves from y equals x up to y equals 5. Like that. And what I want to add up is my probability, and my probability was c times x squared plus xy. Okay. And that's the reason. The reason I've chosen that region is that everywhere else it's 0. So let's see. As with most things, you do the inner brackets first, and you can imagine your integral as a bracket. So that's what I'm going to do. So this will be a definite integral, and it will go from y equals x up to y equals 5. You'll notice that what I'm doing is I'm telling myself which variable everything belongs to, rather than just putting the numbers 0 and 5, so that I don't get distracted and miss it out later. Okay, so when I integrate things, I'm integrating with respect to y here. So the x counts as a constant along this line. As I move up at this line, the x stays the same, so the x counts as a constant. And the c is a constant too. So c is a constant multiplied on, so it will still be there. X squared is a constant, so if I had like a constant like 4 or 7, it would attach a y to it normally when I integrate, so this will become x squared y. And then my x counts as a constant, it's multiplied on, so it's still there, and the y will go up to y squared, a half of y squared. And then I'll sub both of those things in and figure out what that comes to. X equals 0, x equals 5, dx. So let's see, I've got c x squared times 5 plus a half of x times 5 squared minus c x squared times x plus a half of x times x squared. Okay. And now I have a formula that's only involving x. So there's a c in both of them. I might bring that out the front. And then here I've got 5x squared and 25 on 2x. And here, you know what, I might put that c, move that c out later because I'm going to get distracted. And this is x cubed and a half of x cubed, so that's 3 halves of x cubed. Okay. So there is a c there. I've got 5x squared plus 25 over 2x minus 3 over 2x cubed. dx. Great. And so now it is an ordinary integral that involves only x. So I can do it. The c is a constant multiplied on. The 5 here is a constant multiplied on, so it will still be there. The x will go up to x cubed, and I'll divide by the new power. The 25 on 2 is a constant multiplied on. The x will go up to x squared. I'll divide by the new power. The 3 on 2 is still there, and the x will go up to x to the 4, and I'll divide by the new power. And this will go from x equals 0 to x equals 5. And alright, so 5 on 3x cubed plus 25 on 4x squared minus 3 on 8x to the 4. And so that will be 5 on 3, 125. Well, 125 is 5 cubed, but just plus 25 on 4 times 5 squared minus 3 on 8 times 5 to the 4 minus, and if I sub 0 into any of those, it'll all come to 0. Should be careful, sometimes it doesn't. If there's an e to the power of, if you sub 0 in, it won't come to 0. And so I get something ridiculous. I might recruit the help. I suppose I can pull a 5 squared out the front. Actually, that's got a 5 to the 4. 25 is 5 squared, and that's 5 squared as well, so that's a 5 to the 4. So all of them have a 5 to the 4. Not a 5 there, it's only a 1. So that's c times 5 to the 4 times whatever this fraction is. Gosh, a third plus a quarter would be 7/12. Can't be bothered. 1/3 plus 1/4 plus 3 minus 3/8 is 5 on 24. So we get c times 5 to the 6 on 24. Brilliant. And this is supposed to be equal to 1 if it's a valid probability distribution, and so therefore c is actually 24 on 5 to the 6. I'm not going to figure out what 5 to the 6 is, it's better that way. Okay, so my probability density function is actually (24 on 5 to the 6) x squared plus xy. Okay. All right, well, part B asks me to find the probability that x plus y is less than 3. Okay, so what I need to do is I need to find all the probabilities that go with that equation, that fact that x plus y is less than 3, and add them all up. All right, well, let's see. We already had this diagram. We want x plus y to be less than 3. So if x plus y was equal to 3, I would have the line x plus y equals 3, which would go through, well, I just do the x-coordinate, the x-intercept and the y-intercept. When x is 0, y is 3. When y is 0, x is 3. And that would be like this. That's where x plus y equals 3. And let's just check a point 0, 0 is not on that line, and 0 plus 0 is less than 3, so that's correct. So it's actually this bit below the line that I actually want. Which is there. Alright, so let's see, where would this meet? If x plus y is equal to 3 and x equals y, we'll get 2x equals 3, so this is... So x plus y equals 3 and x equals y. meet when 2x equals 3, so x is 3 on 2, and y will also be 3 on 2. Okay. And now what I want to do is I want to add up the volume which is above just that bit there. So I would slice that into pieces. So you want to choose which direction carefully. The best thing you can do is choose a line where you don't have to have different formulas for what the ends are. If I chose my line horizontally, then this end would be x equals 0, and this end over here would be x equals, well, whatever the formula of this line is. And if I chose, and down here, this end would be 0, and this end would be x equals whatever the formula of this line is. So because there's two different pieces that have different formulas, that's not the most efficient one. If I did it as a vertical line, like that, then there is a different formula for the top and the bottom, but I'm always using the same formula for the top and the same formula for the bottom. So at the top here, at the bottom here, my y is equal to x. And at the top here, well, it was x plus y equals 3, so that must be y equals 3 minus x. And so I'll do exactly what I did before. The probability that x plus y is less than 3 would be my little line here moves along the x-axis, and that x goes from 0 to 3 on 2. So it moves along here, and as that line moves along there, then I can move along this line, and that line goes from y equals x up to y equals 3 minus x. And then I'll just add up this thing. And it will be exactly the same procedure as what I had before, only slightly more complicated because I'm going to end up subbing in a y equals 3 minus x instead of a y equals 5. So my formula will be a little more difficult to integrate, but that's what we would do there. So I'm not going to do it all. The 24 on 5 to the 6. And this would be the same integral that we did before, which was x squared y plus a half of xy squared. And it will go from y equals x to y equals 3 minus x. So all of this bit here has become that. And then I'll sub in the y equals 3 minus x, and I'll sub in the x. And that's the point where I'm going to stop and say, well, one could finish it from here. So x squared 3 minus x plus a half of x 3 minus x squared minus 5 to 6 x squared x plus a half of x squared. And then I would integrate that, etc. Okay? And then finally, after that, I've got my part C, which was to find the marginal distribution of y. So to find the marginal distribution of y, I'm doing that thing I did with my Lego, where I'm squishing it all together onto the y-axis. So what I'm doing here is, that's the area on which is defined. I'm going to squish everything onto the y-axis like that. Okay? And given a specific y, say here, that will mean doing an integral along this line here. And that goes from x equals 0 all the way up to this point here has x equals y, because that's what that line is. If my formula for that line was a little more complicated, so maybe it's y equals 3x, I would need to have x equals a third of y. And so my marginal distribution of y will be adding up, or if you like integrating, my other distribution, which was 24 on 5 to the 6 x squared plus xy, along this line. And the thing that tells me where I am on this line is an x. As I move back and forth along this line, or along this line, it will be an x that tells me where I'm up to. So it will be an integral with respect to x. And my x moves, it doesn't matter which direction I go, I'm going to go this way, from 0 to y. And the other way to check that I'm doing the right thing here is if I do an integral with respect to x, and then sub in x equals 0 and x equals y, there won't be any x's anymore. It'll only be a formula involving y, because all my x's will have had something else subbed in for them. So by the time I've finished, this will be a formula in terms of y, and that's good because what I wanted was the marginal distribution of y. Okay, so let's see. It's going to be the result of a definite integral. And the 24 on 5 to the 6 is a constant multiplied on, so it will still be there. This will go up to x cubed, and I'll divide by the new power. The y is a constant multiplied on, so it will still be there, and the x will go up to half of x squared, and I'll multiply by that. And so I will sub in 24 on 5 to the 6, 1/3 of y cubed plus a half of y squared y minus 24 on 5 to the 6, 1/3 of 0 cubed plus a half of 0 squared y. And that will be, well, that bit's 0. And I've got 1/3 of y cubed and a half of y cubed, and so that's 5/6 of y cubed. And so that's, well, let's see. That will cancel with one of those, so I'll have a 5 to the 5, and this will be a 4, because 24 divided by 6 is 4. And that is my f of y. And I could check it if I wanted, and integrate this from y equals 0 to y equals 5, and it should come out to 1. And in fact, you'll notice that it would have been much easier for me to do my original first integral in this order and do the y's and do it along the horizontal lines because my integral was easier to do afterwards. So there's no guarantee that that's going to happen, but this has more x's in it than y's, and so it's usually easier to do the x integral first because there's more x's. And those x's will be replaced by usually numbers, at least some of them will, and so it will be a little easier there. Alright, so there's some things about bivariate distributions and the integrals. Let's just go back and look at the decisions we made, because when you do any sorts of problems, it's important to figure out where the decisions were made so that you could know what to do when you need to make those decisions yourself. Okay, so when I drew my region, one of the things that I needed to do was figure out where the region was, and a decision that was made there was to draw the lines and then sub in a point on either side so that you could figure out what wasn't part of the region. And that's something that most of you would have done back in Maths 1A when you did convex sets. The second decision that was made was whether to integrate along vertical lines that move or along horizontal lines that move. And the decision is usually based on which integral is going to be easier. So if there's more x's than y's, go along horizontal lines because your x's will get bunched up into y's first. But if it's the other way around, do that. And when you do draw your lines vertically or horizontally, then your vertical lines, you have to figure out where the y coordinates are, where they meet the edges of the set. And you always do the ones that are plain numbers first and then the ones that are variables. And you imagine that this one on the outside is the line that's moving back and forth, and this one is moving within the line itself. when you do a probability you need, of a specific combination of x and y, what you need to do is draw this region and figure out what it would look like when x plus y is less than 3. And that's a region on the diagram. One of the best ways to do that is to rewrite this as an equals and do exactly what you did originally. You need to figure out where this meets the edges of your set, and then you have a decision as to whether to do it horizontally first or vertically first. And it's best to try and do it so that you don't have to do two different answers. If I had done it horizontally, I would have had to do two separate integrals, this bit here and this bit here separately. And then finally, when you do marginal distributions, the decision is made for you. When you're doing a marginal distribution for y, everything's bunching up onto the y-axis, and so you're automatically doing horizontal lines. And that means that the x, which tells you where you're up to on this line, is an x coordinate, and so it'll be a derivative, an integral with respect to x. And actually, you can also have an alternative way of remembering it, figuring it out, and that is because when you do an integral with respect to x, all the x's will disappear by the end, and there won't be any x's left, so it will only be in terms of y, which is what you're aiming for. There you go.